Hello everyone, welcome back to my YouTube channel. Today we are going to discuss about eye diagrams in high-speed digital design systems. This is the part 2 of the eye diagram series. Today we are going to discuss about asymmetrical eye diagrams. What are the causes of asymmetrical eye diagrams? How we can improve them and what are the signal integrity insights? You can go ahead and check the part 1 of this video series on my YouTube channel. Let's get started. So before we move on to the asymmetrical eye diagrams, let me give you a few of the terminologies related to eye diagram. In the diagram on the right, as you can see, there is an eye diagram in which numbering has been given from point number 1 to point number 9. Let us see all these points in detail. So the first point is the zero level. Zero level is this one. As you can see, the zero level is the measure of the mean value of logical zero of an eye diagram. Logical zero stands for low voltage or the logical zero voltage. Then comes the number two. Number two stands for one level. One level is the measure of mean value of the logical one of an eye diagram. That means the mean of all these signals over there is considered as the level one. Then comes the rise time. As you can see in the number plate, number 3 is the rise time. Rise time refers to the signal transition from low level to high level. Whenever a signal is traveling from low level to high level, from logic 0 to logic 1, at that time the distance or the timing between or the time taken by the signal to start from 10% to the 90% of the signal is considered as the rise time. Then comes the fall time. The number 4 is fall time. Fall time, whenever your signal is transitioning from signal level 1 to signal level 0, at that time, whenever how much time your signal is taking from 90%, from coming down from 90% of the signal to the 10% of the signal, that is considered as the fall time of the signal. The number fifth is eye height. I haven't provided any definition for eye height because I want you guys to put down in the comment below what is an eye height as per your understanding. Then comes the eye width. Eye width is considered as the measurement of horizontal opening of an eye. As you can see, this is the horizontal opening of an eye. And in an ideal case, the eye diagram or eye width would be measured between the crossing points. As you can see, this is the crossing point. This is one crossing point. This is two crossing point. But in a non-ideal condition, there is some sort of jitter and skews that will get added to the signal, and your eye diagram crossing will change and your eye width will collapse. Then comes the seventh point, that is deterministic jitter. When I say deterministic jitter, jitter is divided into two major parts. One is deterministic jitter, and then comes the random jitter. So deterministic jitter is the deviation of the transition from its ideal time caused by the reflection relative to the transition. As you can see over there, so there was this crossing point, and whatever the signal distortion is going to happen on this horizontal phase, that is considered to be a deterministic jitter. Then comes the eighth point, that is the eye amplitude. Eye amplitude is basically considered as the difference between your logic 1 and logic 0 level, and it has been taken as the mean value of the eye diagram. Then what you are seeing as number 9 is the bit period or bit rate, or we call it as unit interval. Unit interval is considered as the half. It is just the half of the full eye swing, so it is considered as unit interval. Let us quickly discuss about what is an asymmetrical eye diagram. An asymmetrical eye diagram means the eye isn't balanced properly, either in the timing, that is the horizontal level, or on the voltage, that is the vertical level. There are certain common symptoms of an asymmetrical eye diagram. First is one side is more close than the other. As you can see, there will be a slope of the crossing points, and there will be some sort of uneven rise time and fall time transition. So as I have provided the diagram on the right, this is a symmetrical eye diagram that looks exactly, if you on a vertical level, if you divide it, it will look exactly on the left or on the right side. But if you can see the diagram on the bottom, you will see there is the transition period time has been changed. So let us just divide that into half and let us see how and what is the difference between a symmetrical as well as an asymmetrical eye diagram. So on the timing edge, as you can see, the half of the 50% before this half timing looks exactly the same on the right side. On the left, LHS is equal to RHS in this case. But if you see an asymmetrical eye diagram, in that case, the transitioning is happening after the half, like 50% of it. So that is something which will definitely cause some sort of signal timing errors, as well as it will increase the bit error rate. In the next slide, we are going to discuss more into asymmetrical eye diagrams, how we are going to improve them. Before we discuss about the improvements of asymmetry in an eye diagram, first of all, let us discuss about the causes of asymmetry. What causes the asymmetry in an eye diagram? The first and foremost cause is driver mismatch. When I say driver mismatch, whenever your signal is traveling from your transmitter to your receiver, and there are two transmitters that are sending the sending the signal to the receiver. At that time, if there is no proper length matching, then this is going to cause some sort of eye skew, and ultimately eye skew will result into timing errors. Then comes the second part, that is impedance mismatch. Impedance mismatch happens between your driver to your transmission lines, from transmission line to your receivers, and that cause some sort of reflections in the signal. And that ultimately causes the amplitude level reduction in the eye diagram. Then the third part is the power noise. If your power delivery network is not properly created, in that case you're going to see some sort of voltage drops across your plane in terms of DC as well as in terms of AC. You will need some sort of decoupling capacitors. You may see some sort of issues such as simultaneously switching noise and other, that ultimately causes some sort of timing jitter in the signal in the eye diagram. And now what happens when all these three major parts of an eye diagram that causes asymmetry happens? It is going to collapse my eye. As you can see in the diagram over here, your eye diagram is collapsed and your eye mask is being violated. There are some other ways also to that causes the asymmetry to the eye diagram. The first of them is the rise time and fall time mismatch. If there is a rise time and fall time mismatch, that you are going to see this kind of slope in your eye diagram, and this is going to cause some sort of asymmetry. Then comes the intersymbol interference. Interference happens when previous symbols affect the current ones, current symbols eye diagram. Then comes the DC offset and the baseline wonders. So there will be some sort of unequal high and low logic levels in between this eye diagram that is going to that is going to cause some sort of asymmetry. Then comes the jitter. As I explained earlier, jitter are of two types. One is random and the other is deterministic jitter. Then comes the impedance discontinuities. As we have already discussed about impedance mismatch, that can cause some sort of reflections in the signal, and this reflection can be caused at connectors, vias, or traces, or there is a mismatch between your transmitter driver to your trace or your receiver to your trace. So these are the methods, or these are the ways that usually causes the asymmetry in an eye diagram, and that may result into closing of your eye. Now let us discuss about the other aspects of it. Now let us see how to improve an asymmetrical eye diagram. So the first and foremost way to improve the eye diagram or to increase the betterment of your symmetry in the eye diagram is the equalization techniques. So equalization techniques can be used either at the transmitter or at the receiver end. When we talk about transmitter, there are three type of equalization techniques that are being used. One is pre-emphasis, then comes the de-emphasis, and then comes the FFE. FFE stands for feed forward equalization. At the receiver end, there are also three kind of equalizations that can be used. One is FFE, feed forward equalization. Then comes CTLE. CTLE stands for control time linear equalization, sorry, continuous time linear equalization. Then comes DFE. DFE stands for decision feedback equalization. So as you can see a diagram on the right, before we implemented the equalization, my eye was completely closed and my contour was looking bathtub contour was looking very much stringent. But as we implemented the equalization techniques on it, as you can see, my eye diagram symmetry has been improved as well as my eye diagram has been opened. The second most important thing to improve an asymmetry of an eye diagram is the impedance control. If there is no impedance mismatch throughout your channel, then there will be a better eye opening that you are going to see. Then comes the power integrity improvements. If your power delivery network is properly made, as well as your VRM, your sync, as well as your decoupling capacitors are being properly added, in that case, that will definitely improve your eye diagram, as well as you will be see an asymmetrical eye at the end. That will be an open eye. Then if you wish to improve an asymmetrical eye diagram, there are two more methods. One is by reducing the crosstalk. So the crosstalk can be checked at two ends. One is at the near end, known as next near end crosstalk, and at the far end, that is considered as far end crosstalk. If you improve this crosstalk part, then your eye diagram voltage levels will be like from 0 to 1 level or 1 to 0 level. You won't be seeing any sort of distortions there. And then comes the timing adjustment. If we start working on our setup and hold margin part, then this is going to improve, this is definitely going to our improve our timing as well as the symmetry of the eye diagram. So with this, let me summarize my slides. So the first point is the asymmetrical eye diagrams. The asymmetrical eye usually degrades the signal integrity quality and the reliability of your system. So fixing the asymmetry of your eye diagram usually improves the signal margin and the system level margins, robustness, and the performance of the signal. It usually reduces the bit error rate, that is how many bits are being transmitted from transmitter to receiver, and out of them how many bits were shown as an error. So that can be improved. So it's always advisable to combine your time domain analysis and your frequency domain analysis. When I say time domain analysis, we need to focus on the eye diagram, and then comes the frequency domain analysis. We usually focus on the S parameter extraction, where we talk about insertion loss, Lytton loss, crosstalk, and the time domain reflectometry, that is TDR. So both of these analysis plays an important role in order to create an end-to-end perfectly working or acceptably working channel at the end. I hope this session was useful for you, and thanks a lot for all your suggestions and feedback. Have a nice day.